but 4. Well, what you could do is choose one of those categories as a reference category, say the non-smokers. You could first just compare the 1-pack-a-day smokers to the non-smokers. That's what I did here. If you look at the odds ratio, just using the top 2 rows, the bottom row being the exposed people and the top row being the non-exposed people, 1-pack-a-day smokers' odds of getting disease compared to non-smokers is 1.69 greater. 2-pack-a-day smokers have an odds of getting disease which is almost twice as great as non-smokers. The odds among the 2-pack-a-day smokers is almost twice the odds among the non-smokers. But notice the odds ratio for the 3-pack-a-day smokers is less than 1, suggesting a protective effect, because their risk was only 13%, which was lower than the 17%. So now I'll go back to the question. Does this data suggest that lots of smoking is bad for you, is good for you? Because there we saw the smallest risk group. There we see the odds ratio being less than 1. But notice the number of people we have in this group. There's only 15 heavy smokers, 3-pack-a-day smokers. And 2 of them got disease. 2 out of 15 is 13%. If there was one additional person in this group, 16 people now, and that one additional person developed disease, we'd have 3 out of 16. 3 out of 16 is almost 20%. That's a big jump. That's just showing you how unstable, how imprecise this estimate is among the heaviest smokers. Meaning if we built a confidence interval around this last odds ratio, comparing 3-pack-a-day smokers to 1-pack-a-day smokers, it could be very wide. It would probably contain the number 1, the null value for the odds ratio. Probably there's no statistically significant difference between the 13% in this group of 15 3-pack-a-day smokers and the 17% in this group of 748 non-smokers, because we have so few 3-pack-a-day smokers here. So keep that in mind, that even all the analysis we talked about, when we try to draw inference, sample size is important. That's going to affect confidence intervals and p-value. Now, what I'd like to do is to look at these same 2 analyses using a regression model. But let me just make sure I'm not just talking to myself. So can someone just send me a chat message saying you guys are still connected or I'm still connected? Just so I know I have an audience with me, that I haven't been essentially talking to me and my dog in my picture. Okay, at least, Cecilia, I'm glad you're still there. At least that means we're still connected. So let's move on. And now let's talk about, well, before we do that, here's the conclusions you could reach from that table. Here's your chi-squared test, significant at 0.03. I'm just going to point your attention to another test here, Mantel-Haenszel chi-squared test. Notice its value is not the same as the value for the chi-squared test. Chi-squared test value was 8. Mantel-Haensel's value was 4. More importantly is this column called degrees of freedom. One was called 3 degrees of freedom, one was 1. Even though the p-values look similar to one another, these are actually 2 different types of tests. This Mantel-Haenszel chi-squared test is really a test for trend. Here's another one listed right below it. It's Cochran-Armitage trend test. If we took the p-value from that test, notice it's almost the same. It's the same to 3 decimal places as the Cochran-Mantel-Haenszel test, 2.19. It's essentially the square root of that 4.8093, the Mantel-Haenszel test. Meaning that what SAS has given you on this for this 4x2 table is 2 different tests. A chi-squared test of association, the p-value of 0.0325, and a test for trend with a test. If we go back to the table, both of them are asking the same question. How consistent are the data with the null hypothesis? How consistent is this table with the statement that everybody has the same risk of getting disease regardless of their smoking? Everyone has a risk of 19.68%. Both of those tests are trying to measure how consistent the data is with that statement. And both of them give you small p-values. Neither of them say the data supports the null hypothesis. But the way they're calculated are different. The chi-squared test of association is trying to ask whether the data supports the null hypothesis versus an alternative that says the data doesn't support it. It doesn't say the alternative, if it does exist, has to be of a certain type. On the other hand, a test for trend says if the null hypothesis is not true, in other words, if there is an association, what the association is likely to be is one where the risks of disease increase as you move down this table, or they decrease as you move down this table. Another smoking level. And that's what the Mantel-Haensel test is trying to test, the null hypothesis versus a trend alternative, while the chi-squared test is testing the null hypothesis versus a non-specific, any type of alternative hypothesis. And that brings up an interesting question to consider as an aside. If these were your data, you looked at the relationship between smoking and the risk of getting heart disease, which of these two p-values would you choose? 0.03 or the 0.0283? And just think about that for a second. And notice the 0.0283 is smaller than the 0.03. And report the one that's smallest. The statistical police, statisticians, will say that's the last thing you should do. They should say you should choose the test of significance that you want to report before you look at the data. So you should think, suppose smoking does have a relationship to the risk of getting heart disease during the follow-up period. Do you expect that the association would be one of a trend, that your risk would increase as you smoke more or decrease as you smoke? If so, you should report whatever p-value you get for this test for trend. Otherwise, if you don't know what type of association might exist, the safest route is to always report the test from the chi-squared, the p-value from the chi-squared test. So the choice of which of these two tests you give will depend on what you suspect to be the non-null relationship between smoking and your risk of getting heart disease. That's going to become very important when you build models. Because as I would try to show, when you build a model, you're trying to capture the relationship that a risk factor might have with your outcome in the best way that that risk factor might influence the outcome. So there we're deciding whether to build models that are essentially trend tests or build models which are essentially chi-squared tests of associations. And that's what we'll end up with today. So let's look at some models. Now we're going to do the same analysis, not doing 2x2 tables or 4x2 tables, but by using regression models. Let's start with the binary exposure male. I'm going to use, so we have a binary outcome, 1 if you develop new CHD, 0 if you didn't, so Y is your new CHD variable. X1 is a 1 if you're a male, 0 if you're a female, X1 will be the male variable. We're going to fit a logistic regression model. We're going to be interested in the risk of dying, Y equals 1. We're going to say your log odds of dying is B0 plus B1 times your male status, your X1 status. But just so you'll know, that another way of writing this equation is solving for P. That means P, your risk of dying, or in this case, your risk of developing new CHD is equal to e to the B0 plus B1 times X1 over 1 plus that expression. Mathematically, that's just another way of describing a logistic regression model. But the top one, log odds of disease equals B0 plus B1 times X1 is the usual way you see them expressed in textbooks and in the manuscript. Well, I already mentioned that in this model, the coefficient of X1, B1 will equal the log odds ratio comparing males to females in this equation. So let's suppose we fit this model. It says your log odds of developing new CHD is equal to B0 plus B1 times X. Male is 1 if you're a male, 0 if you're a female. If you use SAS, something we'll be talking about in the coming weeks, this is the output you're going to get. It gives you some fit statistics, and I'll talk about what these things mean in the coming weeks. It gives you a global test, a test of the global null hypothesis. It gives you 3 of them, a likelihood ratio test, a score test, a wall test. And notice they're all very similar to one another. Remember that number 26.305 we saw before for the chi-squared test of association? That's to 99 decimal places the same value as this score test we get from this logistic regression model. Meaning if I go back to the 2x2 table, it takes me a second to scroll back on this screens. I'll go back to the male versus new CHD table. And I said, SAS will give you different tests. One of them is the usual chi-squared test of association. There's that 26.375. That numerically is the same as a score test from that logistic regression model, meaning to 99 decimal places, it's the same number, the same p-value. This other test that SAS would give you that we said was similar, this likelihood ratio test, 26.3807. Notice I'll go back to the logistic regression model.